Hello again. It's Croaky Frog here. Oh, I know. Maybe I'll go back and record these when I feel better so they don't sound quite so horrible. All right, let's go back to our reactions of benzene. So all I showed you before was basically electrophilic aromatic substitution. And I told you that the benzene was the nucleophile and it had to react with a very powerful electrophile. And then I did an example for halogenation. But the reaction is the same. And so I am going to now show you how to make those super electrophiles. All right, let me erase what I had here. Okay, so in each case, the benzene is not very reactive, and we're going to have to tempt it with these super electrophiles. So if we're doing halogenation, and I will just do bromine to start with, we would have the diatomic halogen, either chlorine or bromine, and then you have to have a Lewis acid, and nope, I don't want to draw that one first. I'll draw the iron first. FeBr3. All right, the lone pairs actually go in to the atomic orbital of the iron, and we have created okay, so I showed you this before, but all right, so this one is now positive, this one is now negative, and this is what the benzene sees. So the E, the benzene is truly seeing, is this. All right, for nitration, what we have is an HSO4. So there's my sulfuric acid, and I have my nitric acid. Now I drew them out just a little bit funny so we could see what's happening. But this lone pair is going to rip off a hydrogen from sulfuric, and it is going to create H2ONO2. And guess what? I just made an awesome leaving group. And so that is really what the benzene sees. So E is what the benzene sees. All right. Now, sulfonation is a mix of something called sulfur trioxide and sulfuric acid, or it's called fuming sulfuric acid. All right. So sulfur trioxide plus my sulfuric acid. And this is the one that it sees. SO3H right there. So in each case, I'm using either an acid or a Lewis acid catalyst to force that really positive character. Now the next two, Friedel-Crafts alkylation and acylation, I'm going to do that in a different video, but I'm going to go over to the whiteboard, and we're now going to do a generic example of each one. All right. So let's do halogenation first. We'd have Cl2 and we would have FeCl3. And what is really happening is the benzene is really seeing, whoops, that's a chlorine, this. Okay, so it attacks. That hydrogen is still there, and now I have attached a chlorine. But when you break a pi bond, you have to have that in there. And I'm left with Cl, Fe, Cl3 with a negative. That is the base that will come and rip off the hydrogen. I now have my aromatic compound reformed, plus the HCl, plus I regenerate my catalyst. That is what you would see for halogenation. So, summarized, X2 FeX3 looks like that. Okay, so that is halogenation. Clear this board and I'll do nitration. All right, so we have got a benzene and we've got our HNO3 and our H2SO4. And what we are really seeing is NO2. That hydrogen is still there just like before. And then what is still floating around? Really that HSO4. That's the base. And that is nitration. So generically, you'd see HNO3, H2SO4, and you would just put an NO2 on. And so this one is nitration. And sulfonation and it would attack that positive location. And if you'll notice, it's just the same mechanism over and over. It just depends on which electrophile. And it regenerates the acid. And that is sulfonation. Now, one note about the sulfonation, that is very, very, very sensitive to temperatures and to acids and bases. So you can actually make that reverse or do things that you're not expecting if you have, um, a highly aqueous solution or aqueous solutions in heat. Okay, so just beware on the sulfonation. Okay, so that is halogenation. It is nitration, and it is sulfonation, and it's all electrophilic aromatic substitution, and we just need to recognize those conditions are making our super electrophiles. And let me jump just to a couple of the problems. All right, so I'm going to go past Friedel-Crafts for just a minute. Oh, here we are. Okay, so for each of the following, determine. Oh, nope. Where's my math? Where's my problems? Oh, well, maybe I won't show you because guess what? They are supposed to be right there. Okay, and it was just some problems doing some basic what would happen if you put nitric acid and sulfuric acid. All right, so I will go back and I will make sure those get included on this handout. Okay, in a nutshell, in a nutshell, change colors real quick here. Halogenation sees an X plus, nitration sees an NO2 plus, sulfonation sees an SO3H plus. Okay, that's what the benzene is actually seeing, and then you get to regenerate your catalyst. All right, because there weren't any of those problems on the handout, which I will go and fix, I'm just going to do 2 or 3 of them right here. The nice thing about benzene is they pop out. It's really, really hard to miss them. Okay, so if I'm looking at this one, I've got a benzene, and I recognize these as sulfonation. And so my product is that. And I know that seems too easy, but that's really what I'm looking for. This one, I recognize those as halogenation. And that's all I'm looking for. Okay, now this, it's part of halogenation, but I don't have the Lewis acid. And so in this case, the benzene is not going to react because I have to have the catalyst. I have to have that Lewis acid catalyst in order to make that super electrophile. So don't forget, if you only see the diatomic bromine or the diatomic chlorine, it's not going to be like a regular alkene. It's just not going to react. And last but not least, I recognize that as nitration. And so I put an NO2 group on it. All right. That takes care of everything but Friedel-Crafts alkylation and Friedel-Crafts acylation. Until next time, jolly out.